Another story that is for entertainment, which is not in this presentation. Actually, I'll save it for the presentation. Showtime.
We're good? Okay, good morning, everyone. Day 3 of 3 of VCF East. I think, I didn't count, this is like my 20th VCF overall by now, it's pretty crazy. Thank you for coming out here in the bad weather. The weather cannot stop Atari. So Bill Lange, please come up here and introduce Joe.
Hi, everybody. I'm actually more nervous today than I was yesterday giving my talk.
And he should not be nervous.
So a shout out to Pete Fletcher and his wife Heather. Are they in the room? So Pete and I, we got together, and his wife and my wife Lucy got together and made a donation to be able to get Joe to come out here today to speak for a few hours. So,
I got 3 or 4 hours of sleep on that airplane.
Exactly. He's a busy man. So just on the ride over here, a few of us who are software engineers, we talked about how being engineers, we'd like to work on that one product that impacts people, like a great many people. And so I had a chance to do that working at Bell Labs. I worked on
Oh, yes.
voicemail systems.
You touched a lot of lives.
And I knew every day tens of thousands of people around the world were using my product. But your products, you did the 2600, the Atari computers, the Amiga, and later the USB.
Sort of. Like everything, we all contribute, you know. As Jay Miner told me the first day I went to work for him, success has 1,000 fathers, failure is an orphan.
Exactly. So so we were talking on the way over here that Joe worked on the 2600. A lot of us became brand loyal with the 2600. We moved on to the 8-bit computer. We played a lot of games, but we learned how to program. And we became software engineers, and it created a great life for many of us. And Atari was a big responsibility for that, so I'd like to introduce Joe Decuir. Joe?
I hope to earn that applause. Okay, so I would actually like to finish a book to complete what I would call the J Miner trilogy. This is a book by MIT Press, platform series on the 2600. If you haven't seen it, I recommend it. This is a book on the Amiga by another historian. When I was nominated to IEEE Fellow, one of my 3 endorsers was these guys. The one that needs to be written in between would start with, what are the lessons we learned from this machine? And end with, what are the lessons we learned from the machine I'm going to talk about, which animated this? I gave a talk about those 3 machines 6 weeks ago at VCF Northwest. And that talk is published on their website. So if you go looking for me, you'll find it. And that's good. All right. So I worked in industry for 42 years. Qualcomm bought my company in the summer of 2015. 2 months later, I turned 65. They said, here's some money, go away, don't sue us for age discrimination. I said, okay. Because it had stopped being fun. But I became an IEEE Fellow belatedly for my work on these 3 machines. I had the great honor of nominating Steve Wozniak to be an IEEE Fellow 3 months ago. I think he'll make it. And in my encore career, I do 2 things. I'm the bassist in a rock band. We played last night. And I teach engineering part-time at the University of Washington. Because my motivation is I want to pass on to the next generation how to earn a middle-class living while I still remember what to tell them. Because at some point, either I'll forget or I won't care. My wife keeps looking at me saying, I thought you were retired. It's like that. Anyway, so I want to talk about, it's been 40 years since we shipped that machine. So, I want to talk about how I got here. You'll have some ideas. What we learned from the machine that led to this, what we wanted to accomplish, which is different from what we actually accomplished, what we actually designed in hardware and software, more about the hardware than the software, what happened in the market and the industry, what we learned from that, which animated the Amiga, where we are now with modern hardware, modern emulators, modern application software. I want to talk about partial design credit because there's hundreds of people that I'm representing. I'm just the one who's alive and able to talk because some of them are deceased and some of them have Parkinson's, right? And resources, where to learn more, okay? That's my plan for the day. I like questions. If one of you is brave enough to ask a question, it's probable that several of you others have the same issue in your minds but aren't brave enough. That's a teachable moment. That's good. And as someone who's done a lot of public speaking, whenever I'm giving one of these things, I get 4 objectives. It's like, what is this thing? If you're engineers, how does it work? If you're thinking about who needs this, why, what are the applications of this thing? And if I do a good job on the first 3 items, you'll come out of it thinking, where do I learn more? And you'll walk out of here thinking, I want to learn more. I want to do this. I want to use this application. I want to get something, right? Motivation. It doesn't matter what I actually know. What matters is what you walk out with. Capiche? So, how I got here. Okay, first story. So I got to work on the J minor trilogy of machines. I gave this talk 6 weeks ago at VCF because they were actually all there in the museum. There was one of them set up there to work around the corner from where I was speaking. There was one of those sitting right next to the audience, and there was one of these around the corner in the other direction. They could actually go put their hands on them right there. How I got there? Well, first of all, I was not... This is the guy, he was working for Saunders Associates, defense contractor in Manchester, New Hampshire, right? So he invents this stuff. He figures out that technology is going to allow us to bring the story home. Before then, electronic entertainment is owned by the networks. They decide what's on the radio, they decide what's on the TV, they decide what's on the movie screens, right? We don't own the stories, they do. And Ralph Baer had the insight that he could bring the story home, and the story could be between 2 or more people interacting with this system, representing them, right? So he designed the brown box, and his employer, a few years later, licensed it to a consumer electronics company, Magnavox, rest in peace. So they brought out the Odyssey in 1972. I got to meet this guy in his basement in 2014. He died that year, but I was impressed that he was still building toys. I wanted to talk about old video games, and he wanted to talk to me about Bluetooth Low Energy, because I wasn't a subject matter in that, because he can use low energy to control his toys, right? So Atari was founded by plagiarizing Pong, or plagiarizing the brown box. You've seen all that history, right? So they have a big hit. They say, let's build some more complicated video games. So they build Tank and they build Breakout, et cetera, et cetera. They also separately bring Pong home. So now they've got partial completion of a square. What are they going to fit into bringing the more complicated games home? That's the questions that they were facing in 1975. In 1975, coincidentally, in the summer of that year, I'm walking down the street in Disneyland in Anaheim and I'm 24 years old, and my youngest, I'm the oldest of 5, my youngest brother is 12. We're walking down the street, we hear funny noises, we walk into an arcade, we spend a lot of quarters, on Atari Tank, my first exposure to video games. This was very handy a few months later. So I got hired to finish debugging that. The reason I got hired is two reasons. First one was that I had been studying microprocessors on my own, even though I was working in medical research. I bought a 6502 from Chuck Peddle the same day that Ron Milner of Atari did, and the same day that Steve Wozniak did for what would become Apple I. But I didn't know all that. I just was learning on my own. And my message there, by the way, if you think you know where your passions are, spend some cycles preparing in that space, because that could pave the way for you to jump off and have some great adventures of your own. Get used to the fact that the things that that young engineers might do in the next 40, 50 years don't exist yet, because at that point in history, I was barely familiar with video games. They were brand new. Now, video games are $100 billion a year industry. They're bigger than commercial music and commercial movies put together. This is embarrassing. So we used to joke about paying to work there. You know, imagine a little coffee can with a coin slot and we put quarters in, you know, to keep working. It was like that. So let me step in a little bit into how the 2600 works, because it's an unusual machine. Memory was too expensive at that time in history. So the 6502 was programmatically fast enough that it could do a line buffer rather than a frame buffer. A frame buffer with that resolution at that time would have made, well, let's see, our bill of materials in 1975 to build this machine was $65. Now, for you young people, you're thinking, what does that mean? Well, it meant a 3-to-1 markup, right? So, like, one of the reasons the box for that 2600 is as big and heavy as it is our marketing people went around and said, okay, we're going to charge $200 suggested retail for this thing. Well, let's see. What do people spend $200 on now? And the answer is top-loading cassette tape players and stuff like that, which is actually fairly heavy. We have to make something that's that heavy so that people will feel like they're getting something. The circuit board was only this big. The box was this big. It was perceived marketing, right? So at that time in history, you could buy a decent, modest, new car for $2,000, 10 times the cost of a VCS. You could buy a decent house for $20,000, right? So for us to sell 250,000 of these things in 1977, we're prying a lot of money out of somebody for a game machine. We sold 30 million units eventually, but that was the first ones. So this thing here, this is very early in the process of building what would eventually be personal computers. So how it worked time-wise, for those of you getting your engineer hats on. Okay, so there's this thing called a color clock. It's the color burst carrier in old TVs. They're not legal anymore, but they worked. And it took 228 color clocks for a horizontal line, and then 262 lines to form a 60 hertz frame. And what's happening is the microprocessor controls everything. The microprocessor keeps track of time, and it knows when it should turn on vertical blank and vertical sync. The hardware does horizontal blank and horizontal sync. So while the screen is blank and the beam is moving back up, it thinks about what just happened in the game and turns on vertical sync for 3 lines, and then it processes the controller inputs, and then it thinks, okay, what are we going to display next? And computes all the things that it's going to put up here. And then it spends a bunch of lines, 208 lines, pulling stuff out of memory quickly, doing address calculations, and it waits for horizontal sync to write the stuff into memory and then do it again. So the thing is one giant device driver. That's how it worked. Because later we could afford bitmaps and character maps, which is the next machine. I wanted to put this up here so you can see what we were thinking about in the time we were developing this thing. So this is the insides of it. I have a cartoon picture of 3 old video games, and the Atari 2600, the little bubble coming out of it says, "I have no memory." Because this thing, you could put a 2K or 4K cartridge into it, but this thing here had 128 bytes, not kilobytes, megabytes, gigabytes, 128 bytes of memory in this thing. So we bought this off-the-shelf chip which had some RAM, some I/O, and a timer. And we designed this thing called the television interface adapter to generate video and audio outputs. We cut off some of the pins of a 6502 to call it a 6507, and we had a cartridge connector. By the way, I think that Atari retroactively made a huge mistake in 1977. Have you ever heard the expression that premature optimization is the root of all evil? So we're trying very hard to make this affordable. And we saved 50 cents in 1977 by putting that in a 28-pin package rather than a 40-pin package. And we save another 50 cents by putting a 24-pin connector rather than a 30-pin connector. And it would have cost us money in each of the cartridges too. But I believe that if we had done so in 1977, we could have evolved this design to a computer rather than having to make a clean break and starting over with our second system. We anticipated in 1977 that we're going to sell maybe 3 or 4 cartridges per 2600. And we thought that competition was going to eat our lunch in 2 or 3 years. So we had to hustle to get the new machine out quickly, right? In fact, we sold 30 million units in 10 years, and on average, people were buying 6, 7, 8 cartridges each. When you build a platform that is that successful, the customers own you, and you walk away from backwards compatibility with that customer base at your peril. And that's what we did. I've had this argument with Bushnell and Alcorn several times. They don't agree with me. Whatever. Anyway, we walked away from our customers because we were too short-sighted about where we could go with a roadmap of products. So we made a decision to make a clean break for our second system. To put that in perspective, look around the computer industry. Motorola made a clean break from the 6800 8-bit microprocessor to the 16-bit 68000 processor, which was wildly successful for a long time. We use it in the Amiga. Intel was trying hard to preserve backward compatibility. And so they designed the 8008 in 1974. Next year, they extended it to the 8080 in 1975. That was the explosion of the personal computer industry, right? 16-bit address bus, the whole bit. And when they made the jump to the 16-bit microprocessor to the 8086, they realized that they had been attracting a lot of software attention for the 8080. And they were nervous about what to deal with that. And they struck a compromise. They didn't make the 8088 hardware compatible. Code written for an 8080 wouldn't run on an 8086. But if you took your code in assembly language and ran it through a new assembler, the new assembler could convert 8080 code to 8088 or 8086 code. So when they wrote CPM 80, they had to recompile it or rerun it through the assembler, and it would run on an 8088. This was huge. This allowed a lot of people in the nascent personal computer industry to protect their investment in all the software logic. I talk to my students in my microprocessor classes today. I say, why do we bother with microprocessors? They look at me like blankly. It's to enable all that software creativity, because there are a lot more software engineers than hardware engineers. And people invest in those things. And again, you walk away from those things at your peril. So Intel's compromise was successful. They won the IBM PC business in the early 80s, which is still here. There is hardware compatibility between the i7 or the i5 here that I'm using right now and the 8088 from the late 70s. Okay? Let me step back and get through the rest of this. Too much history. Now, we shipped this thing, and I wrote that, and I did most of that. And here's our first machine, and it's about yay big, right? And we had 4 pairs of controllers. We had the joysticks that we shipped with it, a pair of potentiometers that we shipped with it. These were gray-coated things which we shipped for the driving game. They came with the driving cartridge. These things were little keyboard controllers for basic and word-oriented games, right? So that's what we shipped in 1977. What did we learn from this? Well, the huge thing that surprised us, by trying to be cheap, we managed to put the control of the vertical in the hands of the programmers, who turned out to be a lot smarter than we, the hardware people, realized. So they did all kinds of things that surprised us, even when they first started shipping it, and for years thereafter. So we said, no, okay. So our second system should not simply be a bitmap. We needed to allow the programmers to do unanticipated things and follow the beam and do things down the screen. We had created a platform for the art of other people, and we planned to build that idea into the second system. So we in particular wanted to build a machine that was great at playing games, and you could write games for it on it. At that point in history, nobody had done that before, unless you consider the Apple II breakout implementation a game. But in terms of animation capability, this was an order of magnitude more powerful. But we thought we needed to move fast. We correctly anticipated that the competition was going to want to eat our lunch, and we needed to move fast to get this thing out. So we brought our second system out only 2 years later. We shipped a VCS in the summer of '77, and we brought this computer out in the summer of '79. So we did our second system. So I got lucky. Has anybody ever read Soul of a New Machine? Right, okay. He talks about pinball. If you do a good job at something, you get to do it again. And I was lucky to get the first job. I was lucky to earn the chance to get the second job. So we had a decision to make. Are we trying to make a new game machine? Are we trying to make a new computer? Or both? Well, we actually, jumping ahead, we wound up building one chipset that could be packaged different ways, but insides they were the same. So, what does a better game player need? Well, we were writing the book on game playing, because Atari was first a game company. The companies that went into business against us tended to not be game companies, they were technology companies. The Fairchild Channel F was actually the first cartridge-based video game system that came out. Came out in 1976 or 7. It was early. It didn't sell as many as we did, but it was designed by a technology company, Fairchild, looking for a market for its chips. It wasn't designed by an entertainment company. We had, in the Atari Consumer Division, the tremendous advantage of having all those arcade designers in the next building. They were creating ideas that we could migrate. They were critiquing our efforts. When we started working on this second system, they were all over us saying, put in this and put in that and put in that and the other thing. There's some things that are not even in the slides, like the ability to scroll in 2 axes, right? So we wanted memory mapped video, but memory was still expensive. We originally planned on just 4K of DRAM. We eventually wound up buying defective 16K chips. So the original machines actually shipped for 8K bytes, and they switched over to 16Ks in the late 70s, and in early 80s they switched over to 64K. Because memory was plunging in cost that quickly. But we were, again, trying to get ahead. We wanted to use that memory in various ways. So instead of simply having an Apple II-like monochrome bitmap, well, we saw needs for 4-color as well as 2-color, various resolutions, vertically and horizontally. We thought we wanted to be able to change the resolutions on the fly. If I'm writing a game, I might want to have a score, and then some displays, and then some console, control sorts of status information. You'll see that with Star Raiders. We wanted to have color and monochrome character modes. So thinking about productivity, well, how many characters can we put on a television screen? Answer is about 40, right? So having made the arrangements to pull 8 bits of memory out at a time for 320 points across, we said, hey, we could take the same logic and make multicolored characters, 4 colors in chevrons. So I've got a slide that I'm going to explain that shortly, right? Have more sprite engines. The 2600 had 2 8-bit sprites and 3 1-bit sprites. This one had 4 8-bit sprites and 4 2-bit sprites, which you could dovetail together. We wanted to be able to move the screen in either axis because the game player people, the arcade people, were doing that. Defender is a game that goes this way, and there were several games that went vertically, right? And if you look at games like Adventure, that moves from a screen to a screen to a screen, but it would be nice to rebuild that game with a recognizable avatar in the center and move the whole world around her, right? We wanted to add a simple video coprocessor to do things that are happening repetitively on the fly at the interrupt level and not in the main code. Yes, sir?
You used the word sprite engines there, but we know them as player missile graphics.
Right. The rest of the industry called them sprites. And so I'm trying to harmonize my language a little bit, but yes, you're correct. We call them player missile graphics. If you read Decuir Atari, it talks about player missile graphics. And you should, if you want to write code for this.
Can I follow on to that question?
Yeah.
The player missile graphics, the cool part is if you get hardware collision detection, did that come from the arcade industry? Who's bringing ideas?
I don't know, because I actually had at Atari, at Cyan Engineering, in January of '76, the machine that they asked me to debug did not have hardware collision detection. And I thought, we hardly have any memory in this thing at all. How are we going to do software collision detection? What do I need? I need a bunch of RS flip-flops. That's not going to cost me very much area. So I put in hardware collision detection in 1976. And I later moved down to Santa Clara Valley and discovered that they had hardware collision detection too. So I had simply picked up on the same idea, confronted with the same problem.
Thank you.
Where was I? Yeah. I wanted to be able to change modes on the fly under hardware control. So the Antic chip was, amongst other things, a specialized coprocessor. And it had DMA access, so it could do that. Right? So we had a whole bunch of Antic modes. There's not going to be an exam.
We all know it.
Don't worry about that. But we could go from character maps where, there's 1,000 bytes of character map graphics. Again, we have, and those character maps could be either coming out of ROM, or they could be constructed in anywhere in memory, in RAM, on the fly, and modified on the fly. When I show you what Galaxian looks like, for example, that's stuff modified on the fly. We did monochrome characters, we did color characters, we did larger characters that were 4-color. We had bitmaps that go from 40 by 24 is sort of like what VCS playfield looks like, all the way up to 320 by 192. And to illustrate more what the characters look like, in Antic Mode 2, an A character looks like that. And if you use it in Antic Mode 6, it gets larger, but it's still recognizable as an A. If you do this, it looks crazy. If you do this, it looks crazy. In Antic Mode 4 or 5, this thing, which I call a chevron, now looks like multicolored things moving in different directions. Looks funny here, because that's 1 bit deep. I've got a character I call a duck, right? And it looks funny here, but it looks like a duck, right? So these are different ways of using the same sets of bits in different ways. Now, obviously, you use, ducks or chevrons in multicolored things. Turns out, by the way, that Nintendo replicated this kind of logic in the NES, and not to be quoted anywhere, but the descendants of Atari got some royalties from Nintendo for that. We'll leave it at that. Now, using this stuff. So Doug Neubauer, God, I wish he was here, took bitmap and built flying through space shooting beer cans, right? But also used character modes to display console information for the person flying through space, and use other animation here to give the player a sense about where those targets were. This was such a good original game. Atari was originally not planning to ship a keyboard inside of the game console version. But the customer reaction to that was so strong that they said, we got to put some kind of keyboard in this thing. So the 400 had a keyboard. And I've got a lot of buddies who are 20, 30 years younger than me, for whom the Atari 400 was their first computer. And it didn't feel great, but it worked. So anyway, there's that. I took some pictures because I wanted you to get a sense of what it looks like. We ported a lot of arcade video games. I've got some examples here. This one was easy, really easy. And obviously, you have lines where you're just putting up characters. And then it's easy to use bitmap to make these things in multicolor, right? So that's different colored bitmaps. And we have so many different, I would call them sprite graphics, but player missile graphics. So it's easy to run all those things at the same time and nothing's flickering. If you remember what the 2600 version was like in turn, you understand what I mean. Because it was a machine that was pushed too hard. We really had no idea when we shipped the 2600 that people were going to try to do Pac-Man on it. So it was easy to do Donkey Kong. It was easy to do Space Invaders. You know, these are basically colored characters horizontally scrolling. And it's very easy to, if you're doing your character map in RAM, if one of these things takes some damage, it's easy to change its graphics for just that one damaged character. And Galaxian, whole bunch of things going on. These are character maps moving, and then on the fly, it turns one or more of them into moving objects and then makes them swoop in and come shoot at you. That's how it works. It's real easy. So, games. Now, suppose you want to actually do something useful, like earn your living. So, we wanted to support personal productivity applications. I've got some listed on the next slide. So, obviously, we needed to put as many characters on the screen as we could. We made a decision in 1977 when we started this engineering work. There was no market for color monitors. There wasn't a big market for monochrome monitors. We're talking 77, not in 82, right? So we're stuck with TVs. Being stuck with TVs has two big consequences. One of them is we can't display a lot, and one of them is FCC regulations. We'll get there, right? So, but we're stuck to this. We need a keyboard for productivity. Duh. We need peripheral expansion for printers, for mass storage and communications, e.g. dial-up modems in 1977. People were already starting to do BBSs, right? We wanted desperately slots like the Apple II had and S100 machines. You go out there on the floor for this show, you'll see a lot of things with slots. But we're subject to FCC rules. Now, I'm going to talk about them more in a moment. They were very restrictive on what we could do. So, by necessity, we had to design a serial bus. Again, I'm one of the contributors to the serial bus. It wasn't my idea alone. But I went to management pretty early on and said, look, I can't have slots. I got to have these peripherals if we're going to do productivity. Where are we going to put this stuff? If it's not in the box, it's outside the box. And if it's going to be outside of the box, it's got to be serial. That means we're stuck with having to put another processor inside the printer, another processor inside the mass storage device. So our system is going to be more expensive because we're spreading that cost around and then slowing it down. But that's where we were. So one of the nice things that happened later, I got to be one of the people at Microsoft working with Intel on real USB. And some patent troll decided to sue the USB Implementers Forum for patent infringement and blah, blah, blah. And we looked back and we said, by the way, that was published, shipped, and not patented 15 years earlier. Where were you? That's public art. Get used to it. So I am not the father of USB, but again, success has 1,000 fathers, failure is an orphan. Okay, personal productivity. First of all, everybody knew what a typewriter was. We needed to be able to allow people to write. And the nice thing about personal computers writing is that you don't need whiteout. Calculate. Now, people hadn't yet invented VisiCalc. My buddy Bob Frankson, who spoke here before, is one of the authors of VisiCalc. They wrote it for the Apple II first, and then they ported it to the our stuff. But that was a killer application in business. Communications. In 1978, I read an article in IEEE Spectrum on the Minitel system. Anybody heard of that? Yeah. The Minitel was basically a country-sized prototype of the internet, as we now understand it. And I read that and I thought, my next job is going to be communications. So I left Atari in 1979, as soon as this machine was ready for production, to work on communication stuff, and I've stayed in communications pretty much ever since. You obviously got to manage all those files. We want to educate kids, and I thought this even before I had kids who needed educating. Basic programming for people who wanted to get started, and advanced programming like an assembly in C for if you're trying to do system stuff or complicated stuff. I am still one of these people who speaks C. I have not learned, yeah, there's those, no, but there's so many new ones. I mean, I've learned Python, I know just enough to be dangerous. One of my sons works in Ruby. Right. Anyway, so let's step back. How are we going to build this? Well, we had money. We were generating money from the 2600 stuff, and we said, okay. We thought about building a 16-bit version of the 6502 called the 6509. We spec'd it all out. We got people to bid on it, and then we decided, we're building 3 custom chips. Why put even more schedule risk into it? So we dropped that, but that became the 65816, which wound up in several Apple products. Nice processor.
Super NES.
Yes, Super NES. Right, which is the one that finally caught up to the Amiga in animation capability. All right. We thought originally we were going to have 4K of DRAM, but we started with 8K with defective 16Ks, and we went to, certainly by 1980, we were shipping it with 16K or more. And the 800 was user configurable to 48K first. So we undertook 3 in parallel custom chips. The Antic was the coprocessor. It scooped up all the video stuff and shoved it into the GTIA. And so we built the second chip, which grabbed all that stuff, scooped up by Antic, shoved in, and then displayed the video. And so we had a third chip called the Pokey, as in potentiometers and keyboards, that did scan the potentiometers, scan the keyboard, did audio, and did the serial bus data. And we used one standard chip, the PIO, peripheral interface, for 4 bits of joystick per port, etc. So that's what we built in the system, and what it looks like is that. With permission from the guy who wrote Decuir Atari, Chris Crawford, I have this. So we had standard processor, but faster, 1 new chip, 2nd new chip, 3rd new chip, room for cartridges, room for, where's RAM? Gosh, where's RAM? Oh, here's RAM, right. And more ports, okay? Questions about this before I move on?
Yeah, over here.
Yeah.
Was this developed on the Jolt, or was this after the Jolt?
After the Jolt, right. Oh, yeah.
Is that in your talk, or
Hmm?
are you going to touch on that?
Not really,
Okay.
because there's not enough time to cover everything.
Your original design for the Atari 800 had 36K of RAM, and the right and left cartridges.
36K?
Yeah, one 4K and 2 16Ks. We've got one back there you can look at.
We actually built a lot of them in S100 chassis, these Krememco things. There's a picture of that in his book.
Well, my question is, the left and right card had independent address spaces.
Right.
They didn't overlap RAM in that original design. So did you guys have some?
We were thinking,
for the right card?
we knew we needed a left cartridge, and we were imagining that some people would build a system where there's a left side cartridge which had child cartridges as extensions of the first cartridge. It turns out that very few people used that facility, so in all later systems we got rid of this. But we did start off there with...
Was there some? Did you guys have ideas of what the right card would be used for? Like maybe.
Well, yeah, like education, for example. Some applications turned out to be huge, some didn't. And of course, if you go back in time, this is 1979. The suggested retail price for the 400 was 500 and some change. So it was more than twice what the game machine was. And the suggested retail price for the 800 was close to $1,000. Now, you could buy a decent new car for a little over twice that. So this is not a casual activity. At the same time, an Apple II out of the box with no disk drives was $1,200 in 1979 dollars.
So you mentioned the Pokey, you know, it handles input and sound as well, and I noticed a lot of old systems do the same thing. They put both those functionality on one chip. Is there a reason for that?
Could you repeat that so everybody else can hear you?
Sure. So that the Pokey handles input and sound, and I noticed a lot of old systems do that. They put both those functionalities on one chip. What's the reason for that?
Whatever fits. A lot of the things that drove our architectural decisions were how many pins do we need to support this kind of I/O. And if it's too many pins, then you wind up having to split it up into more packages, even though it's not that much more chip area. Like this system was 40 pin, 40 pin, 40 pin, 40 pin, 40 pin. Okay? When we did the Amiga a few years later, we had 48 pin packages. And then we started using PLCC packages, which were square and had different mechanics that got easier because the 64 pin packages on the 68000 were just basically unusable, right? But pin-out decisions drove a lot of what we did. In the case of the Pokey, this would do keyboard scanning, but for scanning the keyboard, we designed it so that there's two external 3 to 8 multiplexers. So 6 bits come out of the Pokey for scanning, and then a 7th bit comes in from that scanning as the bit that it's sensing. So it took 7 bits driven by logic on the Pokey to scan an 8 by 8 array, 64. Things like that drove us. Make sense? It says attend VCF East, and here I am.
Question. If you had gotten the card slots, would they have been directly on the bus, or would that have been through a different chip?
Well, no, these were on the bus. We did have some buffers in the system. We certainly had buffers in the system because the 6502 was not designed for DMA, and so the Antic had to be able to take over the address bus and get this guy off the address bus. So I know we had at least one data bus buffer associated with the main body of RAM. That answer your question? Okay. Yes, sir. Wait for the mic so everybody can hear you.
So you already had the cartridges, which they're slots pretty much. So why would the FCC give you grief for having an actual expansion slot in the machine when you already had a cartridge slot? I mean, it's same.
We're going to get there. Any moving signals generate RFI. They are antennas whether you like it or not. One of the reasons I'm wearing this shirt is I was teaching amateur radio yesterday. Every wire that moves can pick up or generate RFI. And actually, I'm going to save answering that question for when I get there. But basically, to leap into it a bit, I'd have to go ahead here. Okay. There we are. Nope. Oh, I see. That's the one. We wanted to have slots. Apple would not sell an RF modulator. They didn't make one. There were parasitic companies like M&R Enterprises who made them. and the dealers would install them in an Apple II. Apple IIs were very noisy. TRS-80s were very noisy. PETs were very noisy, but not quite as noisy because they had a metal case, right? But all those things with plastic cases, RF goes right through them. Okay, the rules changed in 1979, 1980, but we were working under the older rules. So using a television set means we're going to be driving live RF back up to a switch box on the back of the TV. So our limits were 1 microwatt per megahertz. When they changed the rules, it was minus 43 dBm per megahertz instead of minus 60 dBm per megahertz. Anybody who understands radios knows that 17 dB of power is a lot of power. So that was a big relaxation in what the rules were. We're going to get to that more later, but that's a 2 millimeter thick Faraday cage around the insides of that box. And it was designed so there's a switch here, so when you completely assembled it, if you opened this thing up, it turned off the power. So this machine is dead if you open things up to start messing with the insides. Make sense? Okay, I probably over-answered your question, but that was important. System software. So 2600 had no memory. This thing has to have memory. What does it need? Well, the first thing it needs is something to manage all that I/O. So people had been studying how OS 360 worked and many computer operating systems work. And so they did a professional quality BIOS from the ground up. For any of you who have ever studied operating systems and APIs, applications, programming interfaces, so they built an I/O control block set of APIs for the system, and that included from scratch firmware to manage systems that were outside on the serial bus, as well as stuff that was native inside the box. And they provided an 8K ROM that was built in, plus an extra 2K ROM, which was the floating point package. So that the basic cartridge was another 8K cartridge, could reference that, but any other any other programs could use the floating point package. So when you write a C compiler, it uses floating point. It doesn't have to make it up from scratch. Basic interpreter. We looked at several kinds of BASIC. We got a bid from Bill Gates. That's the first time I met him. I have a notebook that has his address and phone number in Albuquerque. He moved. So he wanted, his memory footprint was larger than we wanted to handle. So we did two things. We had it written by local people that fit in 8K, but we also arranged for an add-on cartridge. I have one at home, so that if you wrote code for Microsoft's dialect of BASIC on other systems and wanted to port it to this machine, it was straightforward. We wrote our own disk operating system. The people who worked on it also worked on Apple's disk operating system. So you put an Atari 800 down next to an 8-tip, put in a diskette. The BIOS will look for the DOS and load it if it finds it. Okay, so inside of an API, for those of you who aren't familiar with operating systems, this is a beginning to show what it looks like. So code, instead of having to know exactly what the I/O does, talks to the API, the middleware, and it says, I want to either output characters or I want to get characters. So it talks to the editor object inside, so I can read from the keyboard or write to the screen. It can talk to them separately as the screen and the keyboard. If it wants to write to the printer, obviously there's nothing in the box. So it's going to go out through SIO to write characters to the printer. If it wants to get data from the cassette, it goes out through SIO to read and or write data to mass storage. If it wants to talk to the disk, it goes out through SIO to read or write records to the disk. If it wants to go to serial ports, it goes out to the 850 or its descendants and streams read and write. Something I need to actually set up. I actually bought one of those RS-232 Wi-Fi adapters, and I have an 850 at home. I need to get it all to work. Anyway, so I think I've covered this one already. This is the inside of an 800 with the 2 cartridge slots. And all these networks are here to make sure that all these signals that go in and out of these controllers are slow from an RF standpoint. So hams liked these things because they were really quiet. So this is what a system might look like with a 40-character printer, an 810, a cassette, and a TV screen, putting up some imaginary application. What it would look like logically is, here's the CPU, serial I/O goes in and out of the 810, serial I/O and goes into and could come out of an 850. That has a printer port that could talk to a Centronics compatible printer. 9-pin serial ports, you can hook it up to a modem. In those days, that was a big deal. We first standardized 2400 bit per second modems in 1984, whereas we shipped this in 1979. Obviously, we drove video and audio to the speakers. Make sense? So, what did we learn from this? As a game console, we went to a lot of trouble to make sure that you could write good games for it on it. It was the first machine designed that way. And it worked. And as I showed you, it was a lot of good games would be ported to it or were created for it. I don't have a copy of Mule. There's some other old games that are really good on it that were original. Now, the founders of Activision and Magic hadn't yet left. So Atari wasn't afraid of them yet. That happened later. As a computer, massive cost reduction was possible after they changed the rules. Short true story. So it's 1979, and I really want to have slots. I desperately want slots, and I can't have them. What am I going to do? Well, I read an ad in EE Times from TI, and they're selling a 3-meter cable with a fiber optic diode and a fiber optic transistor on it, I think. I can build a thing with slots, and I've got 3 meters of cable to the little box that's going to sit on the back of the TV set that makes RF to put into the TV. That should be enough separation that I can do whatever I want here, and I'm far removed from that antenna so the neighbors won't see it, right? So I told the TI guy about this. His eyes got big. And then Wade Tuma said, nah, the FCC is not going to let us get away with that. Well, a year later, we introduced our machine, and TI introduced the TI 99/4. The 99/4 uses that trick. He went back to Dallas, told his buddies about it, and they submitted that as a design. The FCC would not let them get away with this. In fact, Jim Wright was the Speaker of the House of Representatives at the time. TI was his home district. They went to Jim Wright. Jim Wright lobbied the FCC aggressively. He was unsuccessful. The FCC would not back down. So TI had to slip the 99/4 and re-engineer it to get around the new rules, because all those things were creating radiation. So Wade Tuma looks at me and says, if you had been trying to screw with TI, you could hardly have done a better job. Right. So Commodore 64 They had a bad habit of not paying people. But Apple IIs sold maybe 7 million units, all versions. Atari 800s sold somewhere between 4.5 and 5 million units, all versions. Commodore 64 sold 17 million units, all versions, in their time. So they passed this in the market with lower selling prices. In my opinion, when we had the chance, we should have aggressively in 1980, rather than wait a little while, come up with basically the XL line with simpler shielding because the radiation limits dropped. The other thing is that Apple II and Apple III began integrating floppy disk drives and controllers pretty right away. And when we thought about what our next machine would be, and as the Amiga, we planned on integrating floppy disk drive control from scratch. We also wish they'd built an expansion unit for hardware. If you wanted to have, we built this new machine that had a PBI bus on the back of it. And yeah, now we can do buses. But we didn't do those things in time. So the new radiation limits, yes, 17 dB more power is allowed. So this one has 1 cartridge slot, not 2. It has 2 controller ports, not 4, because people weren't writing a lot of games that needed 4 tanks driving around. Conceal the PBI port in the back means peripheral bus interface. So, my last day at Atari, I stayed at Atari. I had discovered communications, as I said, so I started planning to go start a company to go work in that space. But my loyalty to Atari said, I'm not leaving until this product is ready for production and we have good yields in the factory. So I stayed until June of '79 when the yields were looking pretty good. That's another story for another time. So I drew this in my notebook, and I have this notebook in my suitcase. I was going to get some new processor. We didn't use the Z8000, which was a 16-bitter. We did use the 68,000, which was a monster machine. Dual-ported memory. We wanted to do DMA for serial, for communications, for disks, for audio, for video, obviously playfields and moving objects. We were imagining, if you look at the description of the Amiga, it basically follows this. This is the non-video I/O, and this is the, this pair is the Agnes and the Porsche. Oh, sorry, this is the Porsche, this is Daphne.
Question.
Yeah.
Notice you have the Z8000 and the 68,000.
What are the other? That's a Z8000/68000 class CPU. In other words, a CPU of that type. Now, we started working on the Amiga several years later.
So the question for the record was, I noticed this Z8000 and 68,000. Can you give me an idea why you chose the 68,000 rather than the Z8000?
2 reasons. The main reason was, it was pretty clear to me looking at this history of operating systems and whatnot that the 68,000 was going to be multi-sourced and was a much better machine to write code for than the 6Z. This was a CISC rather than a RISC, but it was more of a RISC than this was. Does that make sense? Oh, absolutely. Does anybody know what an ARM is? Yeah. I teach microprocessors and I teach ARM as well as 68,000 and Z80. Right. Okay, so I don't know how much time I've got, but I'm going to keep going. What? 10 minutes. I might make it. So first of all, I want to talk about...
Hello. Hi.
Yeah.
The Atari 1200 XL came out before the 800 XL. Why did they drop it so quick?
Atari was coming apart at that time in history. The main video game market was coming apart. Atari was starting to hemorrhage a lot of money. And so Atari was broken apart and the consumer division was loaned to Jack Tramiel in the middle of 1984. and the 1200 XL was one of the casualties. The 1650 XL was one of the casualties. There's Kurt understands this. He's got lots of displays about this stuff.
That was my first 8-bit computer, and I thought it was great. I mean,
It was.
it had a great keyboard, and I always wondered, well, why didn't they just fix it?
It was
You know,
a company coming apart and competing with many other things that were better at that point. I mean, 1984, the IBM PC had come out. The Apple II series machines had much better productivity support. The video game business was going to come apart, and Nintendo's NES was going to scoop up the remains and make it a distinct market rather than a combined market. Do you follow what I'm saying? I mean, Jay Miner always said that a great home computer was going to play great games that ran all the way through all the machines that I worked on. The market said differently. The market put a lot of effort into productivity machines, and video game consoles tended to be separate. Nice shirt. Okay, so today you now have machines that can software emulate any of these things. There is new hardware development. I've got some samples here, and there's communications applications, right? So first of all, you're going to publish these things, right? Right, the same way you publish my stuff from Northwest? Right, so people can download these things and hit them. Right, so there's things that emulate these processors now on your PC or your Mac. Second of all, there are new peripherals. So there's this guy in Poland, I don't know how to pronounce his real name, but he goes by the name Lotharek. And I have this guy here, and it replaces an 810. And it plugs in serial I/O, and it maps to SD cards. All the PCs and Macs I know have SD card slots in them. It's easy to read and write stuff that's on there. And one of my favorite gadgets, there's this company called Atari Max, and they make this little gadget called an Atari peripheral emulator. So you hook it up to USB to some machine, plugs in SIO in and out, and the software that runs on your PC allows the PC to perform 3 functions. Obviously, the PC has huge amounts of mass storage, so it looks like a bunch of logical drives, you know, from D0 all the way up to D8 or D7. You can take your printer working through Windows or Mac OS, and that printer looks like a printer to your 8-bit machine. And you can do communications with it. In fact, in the latest versions, it's got Wi-Fi on it. It'll give you serial connectivity to the internet through that. I haven't tested that yet, but I'm told that that's true. I need the upgraded software. Anyway, so you can run on these old machines but have new hardware. Now, modern hardware comes in 2 kinds. Here is a field programmable gate array implementation of that stuff. So it's got one hiding under here. Main board, this cable used for flashing it, you know, Cyclone 5. Got lots of I/O, got lots more I/O. Bought this from guys in Europe. Works. I need to flash it so that for HDMI it speaks NTSC versus PAL. These guys are in Europe, it speaks PAL HDMI, and my machines won't talk to it. Second of all, there is people, Atari Age has got, this is native silicon re-implementation of classic hardware, dual pokies, PBI, cartridges, et cetera, serial I/O. composite video, etc. So those look like these. I like that it does SDIO from scratch here with the I/O board. Here are resources, so you can go find out more about what he's got. I hear that Near Dairy is here. One of my heroes. He's got demonstration videos. Find him. So modern computer. Okay, shout out. This man has been developing a cross-platform communications application called Platoterm. Today, for what do we use? We now have monsters everywhere. iPhone X's or 10s have hex cores. I bought myself 6 weeks ago an S10. I don't know how many cores are in it. The answer is a lot. What? I have an S10, but the question is how many cores are in that processor? It's got at least 4. i4s or i7s are hex or quad cores. They all have lots of video display resolution. People watch TV on them, for God's sake, in HD. And they have gobs and gobs of communication bandwidth. But there's this application that we can use on a lot of these retro machines or in a web browser to connect with each other.
All from the same C code.
Yep, cross-platform code. Right. So, final resources. I want to talk about partial design credits because I'm just here representing the people who are still alive and can talk. I want to tell you where you can learn more and how to reach me. So, partial credits. Obviously, I'm trying to represent Jay. Ron Milner up in Nevada City, California, prototyped the video. I did system design, logic design on Antic. George McLeod, who died a few years ago, designed the Colleen TIA, and then it was renamed the George TIA in his honor. Doug Neubauer designed the Pokey, and he wrote Star Raiders, which drove marketing crazy. The Gang of Four, plus Howard Bornstein, wrote the BIOS software. Bill Wilkinson, rest in peace, wrote Atari DOS. Paul Lawton and Kathleen O'Brien wrote Atari Basic. Scott Scheinman, I wish I could find him, was great. I want to talk to him. He and a bunch of us worked on the SIO, and Doug Hardy designed the 400, and Kevin McKenzie designed the 800 from an industrial design standpoint. There was a whole lot of other people involved that, it's like my middle-aged brain, just, who are these people? I appreciate, again, that the Antic Podcast people have been hunting all these people down. All right? So, to learn more, go to the Antic Podcast, please. Go to the Atari Museum. Go to Wikipedia to learn about, what you can. Here is Racing the Beam. Here's Breakout. Jay's back here. Where is he? Right there. Business is Fun. Or this guy. And
Goes over the weight limit on the airplane.
right. It's about yay big. I consider it the definitive social history of Atari as distinct from technically what happened. Chris Crawford, I want to get him out to the PRGE in October. He lives in Oregon. He wrote Eastern Front, and he wrote De Re Atari, and he's been working in the whole interactive artwork theme for video games for ages and ages.
By the way, Joe?
Yeah?
He gave me the source code to Western Front. I'm going to be putting.
Oh, it's Western Front.
No. He did Eastern Front.
Oh.
But there's also Western Front.
Oh, really?
Never released. He gave me the source code. I'm talking to Kevin.
Oh, we should get that up at Atari Age. Yes. Okay. I've written a series of articles. If you contact me, I can send them to you. As the author, I can send them to you, but IEEE has the rights to these two. So you can't publish them in turn. I have to rewrite them for the web. But these 3 articles I have on my drive here. They also did a design case history in IEEE Spectrum in March of 1983, where they basically brought out the fact that we went to all this trouble to make the machine cheap, but by making it cheap, we gave the controls to the programmers who were a lot smarter than we realized. A lesson to relearn. Me, I got a couple of email addresses. You can find me on Wikipedia. After I did all this work, I worked on dial-up modems, kind of paving the internet. I worked on USB, and I worked on Bluetooth. So, any more questions?
Of all the books that you see there, should I do the microphone? Yeah, do the microphone.
Yeah, so everybody else can hear you.
So, of all the books that you are listing there, which would you say is the most historically accurate?
Depends on the history that you want. If you want social history, business is fun. If you want technical history, depends on which machine. This one has a lot of 2600 history. This one has some Amiga history, but not a lot, because the guy was a historian, not an engineer.
Which one are you holding up?
The Future was here, MIT Press. The one that I want to write would be between these two and would complete the trilogy. This one here has some of the technical history, but mostly it's about the industry from Jay Ladino, about this machine that I just talked about here. You want to get technical, this is how to build code for the 2600. Decuir Atari, which I have in my suitcase, is how to write code for the 8-bit machines. And I didn't bring any how to program Amiga books here, because the TSA people said, this is kind of heavy. And this is a good book to have if you're writing code for this 8-bit machine and you're trying to figure out where everything is, because it's basically where everything is. Does that answer your question?
Yes, thank you.
More questions? Thank you, ladies and gentlemen.
I just have a note that if you want to read, if you want to flip through Decuir Atari, we also have a copy at the Atari exhibit, the XLs. So.
Thank you, Joe. Great job.
Thank you, and that was just like 3 hours of sleep and some coffee.
So thanks.